All right, let's go over question number 5, which is Raz Al Gamal. So really quickly to go over Al Gamal, right? We have two people who want to send each other something, Alice and Bob. They're either sending a message or they're sending some kind of key that they're going to use later on for symmetric encryption. So Alice and Bob both have a private key. For Alice, we'll call that A, and for Bob, we'll call that B. They use these private keys to then generate their public key, which for Alice is called capital A, which is just G raised to the power of her private key. And G again is just some generator G that's a publicly known value. And B again does the same thing to generate their public key. So to send a message, for Alice to send a message to Bob, what she first has to do is she first has to choose some random value R, and then she's going to send her ciphertext in two parts. She's going to send C1, which is essentially G raised to the power of that R value, mod P, of course. And then C2, which is that message M multiplied by Bob's public key to the power of that R, mod P. So to decrypt this, what Bob is going to do is Bob wants M. So Bob is going to get M, take C2, divide that by C1 raised to Bob's private key, something that only Bob knows. And again, this is in the mod P space. So if we expand this, C2 is M times G to the BR. And then C1 is G to the R. When we raise that to the B, we get G to the BR. And we notice this part cancels and he ends up getting M. So that's how Bob decrypts. Okay, with that setup ready, we can dive into the questions. So is the ciphertext C1 and C2 defined in this very same way that we just went over? Is that decryptable by someone who knows the private key B? So knows Bob's private key. So the answer to this is yes. And the reason for that is if you think back to how we got M, to get M, we needed to take C2 and divide that by C1 raised to the B. C2 and C1 are things that are sent out in the public. So assuming that channel that Alice and Bob were communicating through was public and insecure, anyone can see C2 and C1. But what makes this a secure scheme is that this B is something only Bob knows. So when this B gets compromised, now anyone can just generate M. So all they have to do, the decryption formula that we have to provide is essentially this. Okay. Now consider an adversary can efficiently break the discrete log problem. If that's true, can the adversary decrypt C1 and C2 without knowing the private key? So the discrete log problem is what stopped us from essentially taking the log of G to the R mod P to get this R value, right? If we usually, right, if we're just dealing with regular numbers, when we take the log of this, right, by log rules, what we get is R log G. But what the discrete log problem says is that this operation is very, very difficult to do in this case because this mod P is a very big, large prime. It's a very large prime number. And when that constraint is added, doing an operation that looks like this is very, very difficult. It's computationally infeasible. So if, right, that is no longer an issue, which is what this problem is talking about, can we find the ciphertext? Can we decrypt the ciphertexts? So when the discrete log problem no longer holds, then our encryption scheme, El Gamal, is no longer secure, right? Because you can just get every hidden value that we hide you by taking that hidden value to the power of G. For example, Alice's public key was just G raised to the A. And when the attacker sees this, they don't have a way to get to A because of the discrete log problem. But now they do. So A is no longer private. And then like the whole security of the whole secureness of this El Gamal scheme goes to the bin. So this is definitely now decryptable because an adversary can essentially get R by just taking, the log of the first ciphertext, right? This R is now something they can find. And then they can also take the B from G to the B because now this B will now be findable. So again, right, we can relate this to the previous problem. They have a way to get to B. And if they have a way to get to B, they have a way to get to M. Okay. Now let's go over the very last part of this question. Now the adversary, we are assuming, can efficiently break the Diffie-Hellman problem. Can the adversary now decrypt C1 and C2 without the knowledge of any private key? Really quickly, Diffie-Hellman, right? Again, we have Alice and Bob with the same private key, the same public key. Alice will send her private public key, Bob will send his private public key, and for them to agree on a message, all they have to do is take the public key that they're receiving and raise that to the power of their private key. So what Alice will produce is B to the A, what Bob will produce is A to the B, and we can notice that, for instance, A to the B is just G to the AB mod P, and B to the A is just, again, G to the AB mod P. So they end up agreeing on the same value without having to send over their private keys. So now we've assumed that when we say that we can break Diffie-Hellman, we have a way to get from components to their creation. So essentially, right, given two values, G to the A and G to the B, the attacker can have a way to find G to the AB. Essentially, what we're saying is that exponent is no longer hidden to them. So if that's no longer hidden to them, then they can use this same principle to break G to the BR. And they can essentially recover G to the BR from the two components, G to the B and G to the R. This being C1, this being Bob's public key. They have a way now to find BR from this. That's what we've assumed here. So because that's the case there, and this setup here looks very similar to the Diffie-Hellman problem, this answer is also yes. And now the attacker can decrypt C1 and C2 if the conditions upheld by Diffie-Hellman are no longer true. All right. All the best with the rest of this paper. Thanks so much for watching.